Today we'll be covering the second part of the definition of a derivative. If you recall from the first video, we talked about the definition of a derivative for any value of x. So we defined our definition as f prime of x. If you don't entirely know what I'm talking about, I recommend you go take a quick look at part one. If not, great, let's continue. So in this case, instead of looking at the derivative for any point x on the function f, we're going to look for the definition of a derivative at a single point. In this case, that point is a. So the major difference is that this is at a point. Okay. The procedure for kind of discovering how we end up with this formula is very similar to the previous definition in part one. The only difference now is that we're working with the letter a, which is a point along f of x. With that said, let's start with our basic analogy, which we used the average velocity for, and it's the same one we used in part one. So the average velocity is defined as the change in x, or the change in position, over the change in time. And that is the final position minus the initial position over the final time minus the initial time. And if you'll notice, this fraction we have here in our definition looks exactly the same as our fraction right here. And that's because they are the same exact thing, and the principle is the same. So if we look at our function now, and we pick our value f of x, and we say this is going to be f of x, okay, which means that if that's the function value at x, then this value on the x-axis is going to be our x. And let's pick our second point. Our second point in this case is f of a. So we'll put f of a here. F of a could also be on this side too. We could put it over here. It's arbitrary. It doesn't necessarily matter, but we're going to put it there for now. And we're going to call this a. Okay. Now, first difference from the last time. Remember last time we had this distance h between these. In this case, we're not doing that. And the reason is because we actually have a specific point we're looking at. The reason we defined h in the last video is because our second point was with reference to f of x, meaning we started with f of x and then we turned it into f of x plus h. In this case, our x plus h is just a, right? We have a specific point a that is some value on the x-axis that we're trying to look for the derivative of f at. Remember, the major difference is that this is at a point instead of some random value x. It's at a point. It's not a general definition of f prime of x, or the derivative of f. Okay, now let's look at our average change of f of x between point f of x and point f of a, or the function value at x and the function value of a. If we take f of a to be our final function value, so the one that's kind of we trace from here, the farthest one along, we take this as our final value, then we can say that g of a, or the average change of f of a, is equal to our final value of f, and our final value of f in this case is f of a. So we'll put f of a minus our initial value, which would be f of x, and then our final value on the x-axis would be a, so a, and then we would subtract x. Now, you may have realized that we have the same expression, it's just our terms are flipped, right? So if you look at this fraction and this fraction, we're looking at our average change, which again is just this piece of this. And in part one, we said that the major difference between an average change and an instantaneous one is that we involve a limit. So again, we're seeing that same pattern play out. The only difference is because of the way that we defined where f of x and f of a are on this function, we ended up with our terms flipped. Now, the interesting thing that you'll realize is both the numerator and the denominator are flipped. So if you think about this, if we were to multiply the top and bottom by -1, and -1 over -1 is 1, right? So we're not actually changing anything. Then that would cause f of a and f of x to flip. So what I'm trying to say then is that this expression is equal to f of x minus f of a over x minus a. Because, again, if you multiply by -1 over -1, you get that same expression. Okay, now it's time to transform this into our instantaneous rate of change. Now, if you remember from part 1, what we did after we got to this point is we said, okay, if I want to look at the derivative, I need to look at the instantaneous change, right? And in this case, we're looking at the instantaneous change at a, right? If x is some arbitrary value, random value, then if we want to get the instantaneous change, what we can do is we can keep moving f of x closer and closer and closer and closer and closer to a until f of x and f of a are very, very similar to one another. In other words, we can take the limit as x approaches a of f of x minus f of a over x minus a. Because if we take that limit, what we're saying is we're looking at the average change as our x value gets really, really close to a. In the same way that last time, we were looking at our average change between f of x plus h and f of x as the distance h between them got really, really, really small. So in that case, we defined the distance between them as h and said that that was going to get really, really, really small. And in this case, we're saying the same thing, we just defined it differently. So if x gets really, really close to a, we're also saying that the distance between the 2 points are getting really, really close to each other, which is the same thing as us saying that the distance between the points was some number, and as that number got to 0, we were going to get closer to the instantaneous change. So we can now say that the limit as x approaches a of f of x minus f of a over x minus a is equal to the derivative of f at the point a. Now, to do a quick summary of what we covered today, and to also draw some more parallels back to part 1, I'll just run through what we just talked about one last time. So we started off with our original definition, and we kind of broke it down. We started with our average change, this change in the function f over the change in the x-axis values. And then we drew a graph, and we defined our values, f of a and f of x, and then x and a, and we said that g of a would be our average change of f of a. So again, we started with the average change, and then we're going to transform it into the instantaneous change by adding a limit. So we take our final f value, f of a, and we subtract our initial f value, f of x, and then we divide that by the final x value on the x-axis, which is a, and we subtract the initial x value, which is just x. And it gives us this, where our numerator terms are flipped and our denominator terms are flipped. But we said that if you multiply by -1 over -1, which is just 1, so you're not actually changing the math, you end up with the same expression. So these two expressions we have here are equivalent. So hopefully that eliminates any confusion you may have had with that. It's also important to note that multiplying by something that's equal to 1 is often useful when you're trying to simplify some expressions in math. So quick little pointer there. Now, in order to get from our average change to our instantaneous change, we recall from part 1 that we have to take the 2 points that we defined over our average change and move them really close to each other. In this case, because one of our points is at x and the other point's at a, we just have to say that we're going to take the limit as x gets really, really close to a. In the same way that in part 1, we had our distance between these as h, we just said that h had to go to 0. But because we didn't define a variable for the distance between x and a, we just say that our limit is going to be as x approaches the value a. So we take the limit of our average change as x approaches a. So the limit of our average change as our 2 points get really close to each other, and that gives us the change at a point, the instantaneous change at a point, which is f prime of a.